Hello everyone, and welcome to my final update for the online O-REU program at Texas A&M. My name is JAREY Corcuera, and I will be a junior in the Mechanical Engineering Department at the University of Utah this coming fall 2020 semester. The name of my project is Inverting the Engineering Design Process with Shape and Topology Optimization. My mentor for this project is Joshua Robbins, a senior member of technical staff at Sandia National Labs in Albuquerque, New Mexico. The sponsor of my project is the online O-REU program at Texas A&M. And quickly before we jump in, I would just like to thank everyone who has put in the time and effort into creating this program for us students during these times. We are all extremely grateful for your commitment to our future. So first, let us define what a generalized form of the engineering design process looks like. The process begins with a problem definition with design specifications such as achieving a required yield strength with a limited set of materials. This information is relayed to engineers who then begin brainstorming and creating geometries that fit the design specifications and may solve the problem. To narrow down the set of geometries, finite element analysis is conducted to determine which geometry solves the problem and is also the most cost-effective. Communication is then done between engineers and contractors to determine whether to finalize the geometry into a product or redesign. So now with the inverted design process, it is fairly similar to the original process, but instead of engineers creating geometries, engineers create a mathematical definition of the design specifications using software. The engineers then input the definition into a software called Play-Doh, which uses gradient-based optimization and finite element analysis to create an optimized geometry. My first goal for this project was to verify Play-Doh software with various mechanics and transient heat verification problems. Verification problems are PDEs with a closed-form solution. To verify Play-Doh software, I compared Play-Doh's computational solution to the analytical solution of the PDE and calculate if the error is below a certain tolerance. PDEs I intended to use to verify Play-Doh software include the 1D wave equation on the left and the 1D heat equation on the right. My second goal for this project was to showcase applications of Play-Doh through various design problems and simulations. This required usage of Engineering Sketchpad to generate mathematical definitions of the design, Play-Doh to compute shape and/or topology that optimizes its performance, and ParaView to visualize the optimization steps. The first verification problem I crafted was a basic 1D heat equation problem as shown at the top of the slide. This problem considered a 2-meter long laterally insulated copper bar of constant cross-section and homogeneous material. The figure on the left shows the mesh of the bar we used in this problem. The initial condition for the problem is a perfect sinusoidal temperature distribution throughout the bar with an amplitude of 100 degrees Celsius. The boundary conditions are 0 temperature ends, where each face of the bar is 0 degrees Celsius, as shown. Using the material properties of copper, we can now view the results of Play-Doh's numerical solution. At t equals 0 seconds, we can see that the left-hand face, or x equals 0 meters, the temperature is 0 degrees Celsius and gradually increases until the peak temperature of 100 degrees Celsius at x equals 0.5 meters. The temperature then decreases to the bottom temperature of negative 100 degrees Celsius at x equals 1.5 meters. Finally, at the right-hand face, or x equals 2 meters, the temperature returns to 0. These values are what we expect given the initial conditions we established in the previous slide. If we take a look at what the temperature distribution is at 250 seconds, we can see that the sinusoidal temperature distribution is still present, but now with a lower amplitude of around 75 degrees Celsius. This is caused by the dispersion or balance of heat throughout the bar as time increases. After computing the numerical solutions, we inputted the analytical solutions we derived using separation of variables and compared Play-Doh's numerical solutions to the analytical solutions. These plots illustrate these comparisons, and after adjusting the time steps a bit to balance the computation time and accurate results, the numerical and analytical solutions came to be nearly identical. Although these results are astounding, I did, however, find a bug in Plato's software that calculated the numerical solution to be a negative sine wave, even though the initial condition is a positive sine wave. This was a great find, however, because finding bugs like these are the sole purpose of doing these verification problems. We also continue this process for comparisons at t equals 500 seconds, 750 seconds, and 1000 seconds. And what we found was that the analytical and numerical solutions matched each other at every time interval. As shown, you can see how the magnitude of the sine wave decays as time increases. The next verification problem we began to work on, but were unable to complete before the end of the program, was the mechanics 1D wave equation problem. The problem considered a thin, 1 meter long aluminum bar of constant cross-section and homogeneous material. The mesh of the bar that was used is shown on the figure on the left. The bar features an initial position, f of x, and an initial velocity, g of x. The bar is built in on both sides such that the boundary conditions are zero displacement ends. The displacement of the bar at any time can be modeled using the 1D wave equation. We were unable to complete this problem in time due to limitations in Plato's software that needed to be developed and tested before being used in this verification problem. Although I was unable to pursue my second goal of showcasing applications of Plato due to many technical problems and a large learning curve, I was still able to learn a plethora of technical and soft skills. One of the most important technical skills I believe I learned during this program was scripting in Linux. Prior to this program, I had no experience in using Linux, so learning the syntax and rules will undoubtedly prove to be a large asset in my future. Another tool I learned to use was GitHub, which allows widespread and easy to share software development and collaboration. This program showed me the power of GitHub and how it can help me become a better software developer. The program I also became acquainted with was PeerReview, a data analysis and visualization application that can be utilized in almost any engineering field. I used this program to analyze the numerical results of verification problems in Plato. Other complementary programs I learned include CMake and Engineering Sketchpad. However, the number one skill I believe I learned during this program was how to endure and overcome unexpected challenges that may arise during any scientific or research pursuit. Many times throughout the program, my mentor and I both ran into problems that were seemingly out of our control. However, through great determination, compromise, and critical thinking, my mentor and I were able to turn these challenges into stepping stones and progress as far as we could. This, I believe, is the best lesson I've learned from this online O-REU program. To summarize my research project this summer, I developed a transient heat verification problem for Plato's software and nearly completed a second mechanics verification problem. I was unable to showcase interesting examples and applications of Plato's software, creating optimized geometries. However, there is a possibility I may intern at Sandia National Labs next summer and solely pursue this goal. And finally, I learned a vast amount of valuable and powerful skills through this program that will surely help me in my future endeavors. Thank you for listening to my final presentation, and go Utes!